All right, cool. So yeah, once again, welcome everyone. Thanks for coming. We'll be talking about exoplanets this week. As always, please sign in. Next slide. Yeah, take the time to sign in. If someone could drop the link in the chat, that would also be helpful.
Also, join our Discord server if you haven't already. I think most of you or all of you are already in there. But, you know, it's a good way to communicate and stay in touch more informally than just over email.
Yep. Could you go back to the sign in? I think.
Yes. Yeah.
A little bit more time. All right. We can go ahead, I think. So yeah, join the Discord. And then can continue. As most of you should have seen, because you should be reading our emails, we have tallied up the votes for our election last week, and we have our new e-board as shown here. So Henry is our new president, Ishida is our new vice president, Harry is still our stellar secretary, and then for the new people joining our e-board, Rob has won the treasurer position and Lena won the public relations position. So congrats everyone. Let's give them a applause emojis. There we go. Claps in the chat. So yeah, I think this will be a great board next year. Hopefully they'll bring continue lots of great things for you all the next academic year. For those of you who unfortunately did not win the election, if you're eligible to run again next year, I highly encourage you to do so. And if you aren't, still please be a member anyway. Unfortunately, in the past, we've had a trend of people who lose the election stop coming to club meetings. But I think that you're all great members and you should all continue participating in the club in any way that you can. So yeah, get to know these faces because there'll be faces that you'll see a lot more often. Unfortunately, Eyal and I are going to become relics of the past after next week's meeting. Next week is our last meeting of the semester, by the way. It will be it's typically one of our more fun meetings. We'll have Jeopardy. So we'll be doing Jeopardy on topics that we've covered throughout the entire academic year. So make sure you come out and play. Unfortunately, we don't have prizes for you this year because one, they took away the rest of our budget, and two, we're not all meeting, obviously.
Actually, I had an idea for a prize we could have. Members of the winning Jeopardy team will get a special name badge in the Discord server. So like when you click on their name, it'll be a different color and it'll show up as a Jeopardy winner. So
okay, that's cool.
Yeah, but you know, no physical prizes.
Off that prize, join the Discord. Yeah. So we have some space news for you. So first thing for space news, I tried to come up with the most onion article sounding title that I could. Hubble just watches as innocent comet disintegrates. So the comet Atlas, formerly known as C2019Y4, was discovered at the end of last year, December 29th, by the Atlas Survey, which it stands for Asteroid Terrestrial Impact. It's basically last alert system. So basically, if we're about to be struck by something, this is meant to be able to tell us at the last second. But yeah, it was discovered at the end of the year, and right after its discovery, it started to brighten very quickly. But as people were observing it in around mid-March, they noticed that it began to dim, and it was later confirmed that it actually broke apart into a few pieces around 91 million miles from Earth. So Hubble last week spotted around 30 fragments of it, which you can see in the image to the right. And few days later, it only spotted 25. So kind of shows you that these are changing based off of their orientation to the Earth. So like different parts could be reflecting different amounts of light, and so we can see them better or worse than other pieces. And so by studying this, some astronomers are starting to get a better sense of how comets break apart and how often they do. This was previously thought to be a pretty rare occurrence, but now they're starting to think that it might happen more commonly. And if some of these fragments stay on the original trajectory course of the comet, they could be observable to the naked eye in the coming months.
All right, so today NASA announced that they've selected 3 main companies to start designing their human lunar landers for the upcoming Artemis mission, which they are planning to send and hopefully land by 2024. The 3 companies that were selected were Blue Origin's, Dynetics, and SpaceX, and they have a 10-month study contract with NASA to design a human landing system, or HLS, to have different designs for landing on the moon. Blue Origin is part of a giant, like a more bigger national team that is consistent of another couple of American companies. And what their design focuses on, that's the top one on the right side. Their design is more focused on for a descent module, and other systems and other companies are going to contribute to that. So that's their design. SpaceX's design is shown on below that one, and their whole thing is that they're going to use the Starship vehicle for landing, as well as using their super heavy boosters that will be fueled by other Starship vehicles. So they're going to like bring a whole package set to the game. And on the bottom left is the Dynetics module design, which is a single module that could do both descending down to the surface and ascending back into orbit. And so NASA's going to work with the 3 companies, and they're going to have the designs more studied, and they're going to have it more polished. So by the end of the 10-month time period, they're going to have a better, more refined design to pick for the actual lunar landing system.
Right. A little bit ago, like 2 weeks-ish ago, a study came out that apparently Oumuamua, that object, that weird object that came from outside our solar system and kind of just passed by, apparently it might have been created by a breaking up, by the breaking up of a larger object. So the idea is that Oumuamua is a pretty rocky object, which is not exactly what we might expect. We might expect more of like a comedy object coming from deep space, and it's also pretty elongated, as you can see in this picture in the top right. So a new study suggests that this was actually that one possible reason that Oumuamua might have these characteristics is because it was created when a larger body, like a super Earth or something like that, went by a star and was ripped apart by tidal forces. So tidal forces, if you don't know, are the forces, tidal forces come from the difference in the force of gravity from one point to the next. Because, for example, if you're closer to a massive object, the force of gravity is going to be higher. If you're farther away, the force of gravity is going to be less. And the net effect of that is a stretching sort of force, which is exactly what you can see in the bottom right photo. So the idea is that a rocky object might have gotten stretched by these tidal forces, breaking up into a bunch of smaller rocky objects, one of which might have been Oumuamua. Yeah.
All right, now on to the main part of our presentation, exoplanets, all about worlds outside of our solar system. So a bit of history to start off. The first early theories that exoplanets could exist came from Giordano Bruno and Isaac Newton. Giordano Bruno was a big proponent of the heliocentric model as opposed to the geocentric model. But one of his other major ideas at the time was that the stars in the sky were other stars like the sun, that they were essentially the same thing as the sun, but much, much farther away. And he thought that if there were other objects like our sun, then there could be other planets like Earth and all of the other planets that orbit the sun. And Isaac Newton agreed with this idea. He also thought that if stars were other suns like our own, then they would probably have planets like ours does. And then jumping forward into the 1900s, Otto Struve, a Russian-American physicist, predicted that Doppler spectroscopy and transit imaging, which are two methods that we'll talk about in a little while, would be able to detect superjupiters, which are planets that are the size of Jupiter or much larger. So he was the first one to posit that these methods could be used to detect exoplanets in the future. And he ended up being right, and he predicted that about 40 years before the first detection.
So the very first detection of an exoplanet is actually a bit of an underrated one. I'll talk about a more overrated one in a second, which was the second detection. But this very first detection was actually around a pulsar. For anyone who doesn't know or needs a bit of a reminder, a pulsar is a special type of neutron star. So this is a stellar remnant after a massive star dies, it can leave a neutron star. And so this special kind of neutron star has a very strong magnetic field, and charged particles can get caught in the magnetic fields. And what that results in is basically a lot of light being emitted out of the poles. And now as the pulsar rotates, that really intense light could kind of be directed towards the Earth, or it could not. And so that means that as it's rotating, the pulsar appears brighter and then appears dimmer. And the rotational speed is very regular in pulsars. Some pulsars are slower, some are faster, some could be rotating hundreds or even, I think, thousands of times a second. They could be very, very fast, but very regular. They don't, an individual pulsar isn't going to vary much in its rotation as you look at it. In fact, they can be so precise that they could actually be used to keep time more accurately than an atomic clock. So what that means is that when you observe a pulsar and now you see its rotation varying, you can figure that something's going on there. And so the conclusion is actually that a planet might be orbiting it. We're going to talk more about this later, but the effect is kind of like Doppler shift. So when the neutron star, when you have a planet orbiting the pulsar is going to be moving a little bit as the planet moves around it. And at one point in time, the pulsar might be moving slightly towards us. And in that moment, the rotation seems to be going faster, basically because of Doppler shift. And then when it's moving away from us, it seems like the frequency is lower. Just like how if you have an ambulance passing by you on the highway, as it's coming towards you, the frequency of the siren is higher. And as it's going away from you, the frequency of the siren is lower. And so basically by analyzing that, that's how the very first exoplanet was detected. Initially in 1992, 2 exoplanets were detected. I say planets C and D over here because the convention for naming planets is typically that the star they orbit around is considered the object A, and then going outwards, you have the objects B, C, D, and so on. And the one that was the planet closest to the star was actually just detected in 1994, a couple of years later. So that would be planet B. And so their names are Poltergeist, Phobator, and Draugr. I don't know if anybody happens to know what those are, but I think they're all kind of like undead related things because the pulsar that they orbit around, PSR B1257, is nicknamed Lich, which is an undead creature. I'm not really sure why they named it that, but I like to imagine that it's like a neutron star is a dead remnant of a star, and having planets around it gives it life again. Anyways, it's kind of a special detection. Even after all this time, we detect exoplanets all the time. Just about anywhere we look, we detect exoplanets. But of the thousands of pulsars that we know of, only 10, actually less than 10 exoplanets have been confirmed. But there's thousands of confirmed exoplanetary systems around normal stars. All right. Thanks. So the second exoplanet system detected is the one that is most recognized and the one that actually had a Nobel Prize awarded for its discovery. So before, we say how unfair this is, there is actually a reason for this, and that's that this was the first detection around a main sequence or a sun-like star. So a neutron star is obviously a star that's very different from the sun, and a big part of our interest in exoplanets might be that we want to see if there's life elsewhere in the universe. And we're probably not going to find life around a pulsar, but if you have a star that's similar to the sun, that seems a little bit more hopeful. Also, since so many exoplanets are detected around normal stars, let's say, this was quite a milestone to really blast off all our the rest of the detections that would happen. Since the method is slightly different, very similar, but slightly different than what was used to detect the exoplanets around the pulsar. Again, we'll talk about this more later, but the method that was used was the radial velocity method around this star 51 Pegasi. This was discovered in 1995, so just a few years after the exoplanets around the pulsar. And you can go on to the next slide now. So the planet that was detected around 51 Pegasi is pretty much a hot Jupiter. Again, we're going to talk more about hot Jupiters and what they are later, but it's basically a very massive gas giant that orbits very close to its star. And so this planet is about half the mass of Jupiter, but it's probably actually bigger than Jupiter in volume, in size, because being so close to its star, it's very hot, and that would inflate the planet. You might think that also being so close to the star, it might have like all this gas kind of whipped away from it by stellar winds and things like that. But just by virtue of the mass of the planet, it's able to hold on to its thick atmosphere. It's very, very close to its host star, so much closer than Mercury is to the sun. In fact, Mercury is about halfway, a little closer than halfway from the Earth to the sun. Whereas, so those would be astronomical units. Mercury is about 0.4 astronomical units from the sun, whereas 51 Peg B, this exoplanet, is only 0.05 astronomical units, or 0.05 Earth to sun distances from its host star. So that makes it very hot, and it experiences temperatures of about 1,000 degrees Celsius or 1,800 degrees Fahrenheit. This also really challenged what we understood about planets and planet formation at the time, since, well, if we look at our own solar system, the giant planets are much further out. The closest planets to the sun are these small rocky worlds, and then, the big ones like Jupiter, Saturn, and so on, those are much further away. So we kind of looked at this, and we didn't really understand how that could happen, and a bunch of different theories came up, like, maybe planets migrate after they form, so this gas giant could have formed further from the star and then migrated inward. Or another theory was that this used to be a brown dwarf and it had some of its mass stripped away. That doesn't seem to be the most likely scenario, but we really had to rethink how planets could form. And eventually we would discover a lot more planets like this, and this would really challenge how we think of planet formation.
All right, so now sort of moving on to the modern era of exoplanet detection. The biggest, exoplanet mission that we've had so far is the Kepler Space Telescope, which was launched, and its primary purpose was to look for exoplanets. It was launched in 2009 and retired just a couple of years ago in 2018 after its reaction control system ran out of fuel, meaning that it's no longer able to sort of stabilize and reorient itself in space. But during its 9-year mission, it observed over 500,000 stars and discovered 2,600 exoplanets. So that greatly increased the number of exoplanets that we knew about. And this worked using the transit method, which basically is looking at stars and waiting for a dip in the light when a planet passes in front of it. And the way that Kepler did this, basically you need to look at stars for a long time to have a good chance of detecting a transit. Because if you're talking about planets that have year-long orbits or multi-year-long orbits, then you're not going to see those if you just look at a star for a day. You have a much lower chance of seeing those. But a lot of the planets that Kepler detected were hot Jupiters, which, like we talked about, are Jupiter-sized planets or larger that are very close into their star. And that makes them easier to detect because they're bigger. and also because they have shorter orbits. So they're going to pass in front of that host star much more often than a planet that's further out and only passes in front of the star every 80 years or something like that. You're much less likely to even be looking in the right place at the right time to see that orbit. And then you can see on the bottom image here, this is the Milky Way across the sky, and this region here is the region that Kepler looked at for those 9 years to detect exoplanets. So it's sort of inwards on the disk of the Milky Way galaxy, because that's a much denser region of stars than if you were looking sort of up, down, or outward in the disk of the Milky Way. So that's why they chose that region, was because it was a dense region that had a lot of stars. So Kepler could watch a lot more stars without having to move around. And then sort of the successor to the Kepler Space Telescope is TESS, the Transiting Exoplanet Survey Satellite. That was launched in 2018, and it uses an array of wide field cameras like Kepler did. But instead of just looking at one region of the sky, one small region, it's actually going to rotate and cover, I think, about 85% of the sky. So it has a much wider search area. It should be able to detect smaller planets than Kepler was able to, which are interesting to us if we want to find Earth-like planets that could potentially support life. We want to be looking for smaller planets, things that aren't Jupiter-sized, because those are going to be gas giants and they don't have a solid surface. Some of the interesting discoveries it's made so far it has about 1,800 objects of interest, which are potential exoplanets that haven't been confirmed yet, but are basically candidates for further study to see if we can confirm those as actual exoplanets. And one of the most interesting discoveries came just earlier this year. TOI 700d was the first Earth-size exoplanet the TESS detected in a habitable zone. And then here is a little animation showing, since 1991, the progress we've made in detecting exoplanets. So you can see it starts off very slowly with those first few that were detected, like 51 Pegasi b and the ones orbiting pulsars. And you can also see the colors correspond to different detection methods. So a lot of those early discoveries were radial velocity detections. And then as we get further in, you'll start to see a lot more transit detections once Kepler comes online in 2009. So if you look at the top left there, you can see that very dense region of purple circles forming. That's the area of the sky that Kepler is pointed at. So most of our exoplanet discoveries are in that area of the sky, and Kepler used the transit method. So that's why all of those are purple.
There seems to be a big cluster of a small cluster of the ones detected by microlensing, right where your mouse just was. Is there any reason they're mainly in that region of space?
I'm not sure. I don't know what
That's,
study those were from.
With microlensing,
I mean,
I don't know if this is the reason or not. Sorry, I had my lights all switched around, so I turned off my camera. But oftentimes they'll be grouped together because you need a lens in order to have microlensing, and a lens is just a really big object that like bends the light around it. So the reason that they're grouped together is perhaps they're using like the same galaxy as a lens. Fun fact. I love gravitational lensing. It's so cool.
I think the cluster is also around the center of the Milky Way, if I'm reading the picture right. So that might have something to do with it too.
Yeah, that looks like the center of the Milky Way there.
Yeah, I get, for planets, it'll have to be another object inside our Milky Way. Sorry, I misspoke. It couldn't be like a galaxy that's the lens, because obviously it's inside our galaxy. But really massive stars and other stuff like that could do it. This is a really cool image.
Henry, you're muted right now.
Oops, sorry. Yeah, so I was saying, I wonder if these being all pointed towards the center of the galaxy might just again have to do with the fact that it's a very dense region of stars. So there would be more opportunities for that perfect alignment that you need for microlensing. So maybe that was chosen as a target region for whichever study detected those planets with microlensing.
All right, so we've talked a bit about how we've discovered exoplanets, but let's see how we actually find and detect them. So the first method that we'll be talking about is direct imaging. And as the name suggests, it's just literally you take a system and you directly image the star and the planets. The first, on the top right, you could see a little animation. That is the system HR8799. The center is shown by the star itself, and you see 4 planets kind of moving around it. And the base principle behind direct imaging, as this animation shows, is you literally just take a telescope, point it at something, and then you can use a coronagraph, which is often used in solar telescopes, which is literally just a disk that blocks out the sun or star's light, so you could see the things around it. And it kind of uses that base principle to observe and directly image planets, as with like the Fomalhaut system and the WASP exoplanets that scientists have observed and detected. One important thing to note is that it's very good to use infrared wavelengths when using direct imaging methods, just because many main sequence of stars, like our sun included, they don't produce as much light in the infrared as they do in other wavelengths. So it's a really good technique, and it's a really good wavelength to use for direct imaging. And in terms of thermal emission, you can use thermal imaging to kind of differentiate the planet itself, because every motion has particles, and that's going to cause electromagnetic radiation, which we see as thermal emissions. There are some key advantages to direct imaging. One is that it provides better limits on planet's mass when it comes to like the different equations that are solved out. It's also very good in terms of just finding big, gigantic planets that are usually gas giants and planets that have larger orbits. But a disadvantage is that it works for very specific situations. Again, for larger planets that are kind of farther away from their star itself. A lot of telescopes that are being made are going to try to use more direct imaging processes. Some, like James Webb, use coronagraphs if James Webb ever gets, up in the sky, but the scientists are also working on a star shade kind of instrument, which would basically be kind of like a coronagraph, but more in a physical sense, where there's something literally directly blocking the star's light, and you could observe the planet that way. So something that hopefully will be more improved upon in the future, but as of now, direct imaging is definitely a very good way to observe different planets, but again, a very specific method. Next slide. Another method, and as we saw with Henry, the animation that Henry showed, radial velocity proves to be a very good method for detecting exoplanets. The radial velocity method kind of basically is based on the concept that when 2 objects are orbiting each other, it's not just one moves around the other one. There is a common center of gravity, as you can see with the animation. So what happens is that the star also wobbles as the planet kind of revolves around it, and we could detect the changes that the star will, have to kind of like find the exoplanet itself. If you go to the next image, or like the next slide, you could kind of see how the base principle works. So for those of you who don't know, Doppler shift is kind of based on this principle. So if you have, let's say, a siren or like a car coming towards you, the wavelength is going to be a bit more high pitched, just because the wavelength is kind of contracted, and we call that blue shifted. And as it moves away from you, it's going to be red shifted, so you're not going to hear it as high pitched. The same principle could be applied to light, where if a star and the system is moving towards you, it's going to be blue shifted, whereas if it's moving away from you, it's red shifted. So by looking at the different wobbles of the star and like looking at the spectra, seeing when it's blue shifted and red shifted in a more periodic manner, scientists could use this method to detect exoplanets around certain stars, and it does prove to be a very good method itself. If we go to the next slide, the radial velocity method has advantages. It can find different information from like the direct imaging method, it could find the eccentricity of the planet and kind of gives you a minimum limit on the mass. But the main disadvantage is that it's really limited depending on what plane we're actually seeing the system in. If we see it edge on, we could get the full radial velocity, which is just the velocity towards the direction of the radius. So we have a very good lower limit on the minimum mass. But if we see the system at an inclination for like the orbital plane, we won't get as well of a number. And if it's face on, we don't see any type of radial velocity. So again, there are limits to the system itself and to the method, but it still does prove to be very useful in detections. Next slide. A very famous and well-known method is the transit method, which basically involves a star, and then you have a planet that goes across the star. And we saw a transit, was it Mercury or Venus? I can't remember, but it did transit, I believe last year. And so it basically observes the changes in stellar brightness as the planet transits across the star. And it usually does require near edge on or exactly edge on inclination of the orbit. And it's really good for planets that are close to their stars, so you can see the transit depth really well. If you look at the little animation, you see as a star is there, and then the planet kind of goes across the star, you see that there is a dip in the brightness for a graph, and this dip could help you figure out what the radius of the planet is. And you could also use this information to find like the orbital specifications, like the semi-major axis of the orbit, if you know some other details about the system itself. So very common, very good method, but again, it also has its limitations. Next slide. Not as well known, not as well used, but still really cool method is astrometry. And if you play the little video, it's kind of based on, okay, I'm gonna let the video explain.
Yeah. Does the video have sound?
I don't think so, no.
Okay.
All right, so as the little animation showed, astrometry is a very, very visual technique. It kind of just relies on the base principle. If you have a very precise measurement of where the star is in like the sky, and you keep track of the motion over a period of time, you observe that the star has a wobble, again for the reasons that there's a planet orbiting around it, so the star's position changes slightly. If there was no planet, we would see a straight linear line, but because there is a planet or multiple planets, you see this wobble. And if you did take really good data, you could probably track it really well and try to use that to determine what the planet is and how many planets there are in the actual system. But it's not a very common technique just because it does require a lot of precision and not the most reliable as well. Next slide. And as Erin mentioned before, gravitational microlensing. It's a very fun technique for discovering planets. The base principle, again, relies on, as Erin mentioned, the fact that there is a lens that kind of bends the light and magnifies the planet or the image itself. So as we all hopefully know by now, gravity is just the curvature of space-time. So if light from a background star or just an object kind of goes around it, it creates like a lens if there is a very massive object that also bends the light, and it can magnify the image. So if there is, say, a system where there's a star and a couple of planets, if their image is magnified, it's easier to resolve the planet from the star itself. And it's a really fun technique to kind of find exoplanets. I'm not sure about how many planets have been found using this technique, but I just love it because it sounds really cool. If you go to the next slide, it kind of shows how the principle would work. You have a star, the light gets magnified, and you kind of see this dip, and using that little magnification, you could resolve the planet and the star itself.
Right, so now that we've talked about how we might find exoplanets, we should probably talk about the different type of exoplanets that you may find. So there's really not a whole lot of ways that you can categorize exoplanets into broad groups. Some of the ways is by looking at their distance from the star, and the mass of the planet, their radius, and what they're made of. So you can see in the bottom left a plot. Sorry. Yeah, you can see a plot. And on the y-axis, we have the diameter of the planet, and on the bottom, you have the mass of the planet, which pretty much gives you a density. And through this, we can pretty much show all of the main types of planets, not taking into account where they are in relation to the star. So we have terrestrial planets like Earth. We also have some exoplanets we found in this area, like the TRAPPIST system. We have super Earths and mini Neptunes, which are a bit more massive than Earth, but have different, with the super Earths being pretty much just larger Earths and mini Neptunes being a bit more massive than Earth, but a lot more Neptune-like in composition. We have Neptune-like planets, which are like Neptune and Uranus. We have, and then we have the more Jupiter-like planets. As you can see, we detected a lot more Jupiter-like planets. If you actually look on the right plot, you'll notice we have a similar plot. We have mass on the y-axis and the period on the x-axis. And through here, we can see a lot of the main groups of exoplanets that we've detected. We have some very massive planets with the short periods on the top left over here in green, which are the hot Jupiters. We have less massive planets with a period of about what looks to be like 1 to 100 days. And then in the top right, we have in the red, we have also more massive planets, but around 1,000 days, which are far away from their star. One of the main things to take away from this, though, is if you look at the different colors denote the different detection techniques, with red being radial velocity and green being transits, and with some other methods that we didn't talk about. So this doesn't really represent the entire population of all exoplanets. It's really limited by our detection techniques. If you want to move on to the next slide, Henry. So first, we'll just briefly talk about Earth-like planets and super Earths. So these aren't a super huge amount of the planets that we found, being only a couple %. Earth-like planets are pretty much like the name suggests, similar size, mass, and composition to Earth. But we have found a few interesting systems of Earth-like planets. We have the TRAPPIST system, for one, which is my favorite system. We detected 7 exoplanets around it, with sizes ranging from around 0.3 to about 1.1 Earth masses. And they're around an M dwarf, and they're all really close. And I don't think I put the period here, but I'm actually really close to their host star. They have periods of only like a few days, actually. I think 1 to 20 days around. And on the bottom right, you can actually see how these planets stack up against the solar system's terrestrial planets in terms of their density, which is related to their composition, and the illumination from their host star, which relates to the distance from the star. Because M dwarfs because they're all close range, but M dwarfs also are a lot less bright than our star. And they're actually pretty close, and as you can see in these metrics. Super Earths are like Earth, like I mentioned, but they range from around 1 to 10 Earth masses. You want to go to the next slide. Right, and then we have mini Neptunes, which are similar in mass to super Earths. They're about 1 to 10-ish Earth masses. Uranus and Neptune are about 15. And as it turns out, they're actually the most common type of exoplanet, which I did not know about. If you look on the right, we actually have a plot of some known transiting planets by size. I think this is detected by Kepler, I'm not sure. And from left to right, it goes in terms of radii, in terms of, And you'll actually see that the most popular type of planet found is actually the sub-Neptune size, right in the middle, a bit more than super Earths, which is pretty neat. So, right, so the mass, like I mentioned, is about 1 to 10 Earth masses, but their composition, like the name implies, is more similar to Neptune and Uranus. So what this means is they have a thick atmosphere of hydrogen and helium. They have probably a liquid ocean of water, ammonia, or other volatile materials with small cores. In the atmosphere is around 10 to 25% of the planet mass, which means they have a really, really thick atmosphere. Earth's atmosphere is about a few fractions of a percent of the total mass of the planet. And their minimum radius is about 1.6 Earth radii. I'm going to go to the next slide. Yeah. So now we'll also talk briefly about hot Jupiters. So they're one of the most popular exoplanets we've detected, but they're found around 1% of sun-like stars. The reason that they're so common in our detections, even though there's not that many of them, relatively speaking, is because they're close to their host star, which means they're a lot more conducive to radial velocity methods and transit methods. So they're really close, which means they have a period of only a few days, and they're less than around 0.1 AU from their star, which is about a quarter that of Mercury from our sun, so pretty close. And they have masses around 0.2 to 10 Jupiter masses. But there is actually a lot of debate on how they arrive at their close-in locations. One of the ideas is that they just form there, but because of physics that I'm not 100% familiar with, that's not necessarily super likely. So then the only logical thing that would have happened is they formed farther out and then somehow migrated inwards. And there's a few different ideas for how that might have happened. For example, when it was forming, it formed in a protoplanetary disk with a lot of dust and gas swirling around with it around its host star. That's how all planets form. And during the course of this, it would have suctioned or taken some gas from the protoplanetary disk and dust. And through some exchange of angular momentum, they would have lost some angular momentum and lowered their orbit, getting closer to their host star. And then their orbit would have been circularized by tidal forces. Another idea is that they had some gravitational scattering. They had some gravitational influence from other more massive planets, and that pushed them inwards. In any case, they're really interesting, partly because of the effects of them being so close to their star, what those effects have on the planet. For example, because they're so close, they're usually tidally locked, which means one side of the planet faces the star at all times, and the other side faces away from the star at all times. And because of that difference in obtaining radiation from the star, they can have around 1,000 degree Kelvin difference between the night and the day side. And because of that huge temperature difference, that can drive huge winds around the planet, up to 1 kilometer per second. Hot Neptunes, which are like Neptune-ish like planets, but closer to their star like hot Jupiters, those exist, but they're a lot less common. There's not a whole lot of, from what I've read, there aren't a whole lot of explanations for why. Still an active topic of research. Yeah. So we can also talk briefly about some other types of exoplanets. And we have cold Jupiters and cold Neptunes, which are like our Jupiter and our Neptune in our solar system, which I didn't talk about a whole lot because we know what Jupiter and Neptune are like. And then there's also Chthonian planets, which I only found out about a little bit ago. So the idea is that they're the core of a gas giant that had its gas stripped away. For example, with hot Jupiters, for example, they're constantly bombarded by a solar wind and radiation from the star, and that blasts away their atmosphere, little by little. So the idea is that was such an exoplanet. It could have had its atmosphere completely stripped away and just leaving a rocky core. So this is theoretically plausible, and there are some known exoplanets that may be Chthonian, but we're not entirely sure. It's still an active topic of research. Yeah. Yeah. So this is just a brief thing I wanted to show. It's a pretty complicated plot. We're not going to talk about the vast majority of it, but the main things we should look at is on the left column. Yeah, so in the left column you have the radius of the planets, and on the bottom you have I think masses. Sorry, I'm trying to read that. I got cut off by Zoom. Yeah. And using this, we can see a lot of the different types of exoplanets we can have. So for example, like I mentioned, radius and mass are related by density. So these lines over here, these show the densities, the equivalent density lines. For example, a planet made completely of water would be on this line, the blue line. Sorry, I keep forgetting my mouse. I keep forgetting you can't see my mouse. On the orange line, you see the density of Earth. So Earth-like would be on this line. You see some other lines in terms of density. You have some nice labels, rocky worlds, water worlds, all depending on their mass and their density and things like that. And then the color is the temperature of the planet. So the closer the planet is to their star, the redder it's going to look in this image. So you can see the Earth and, the solar system planets are in here. I just don't know how to show you where they are without using my mouse. But anyway, you can see a lot of the different types of exoplanets we have here. We have a few water worlds. They're not super common because they're low mass. There's a lot of really massive red planets, which is the hot Jupiters, because they're close into their host star. We have a few Earth-like planets. A few of them are red, which means they're closer to their host star. A lot of them are less so. Uranus and Neptune are all in this sort of, I can't show you with my mouse, but in this white region with the other planets. But anyhow, I just thought it was an interesting graph to show off. That's all I have for this slide.
All right, I think that wraps up our presentation on exoplanets.
Yeah. There was also a quick thing, though. I think we talked about a space engine and universe sandbox yesterday.
We talked about those a little to sort of demonstrate. Did you want to use one of those now?
Yeah, so I actually wanted to pose it to my fellow club members. So there's two things I was thinking we can do. So there's a program called Space Engine, which is essentially like a Google Earth, but of the entire universe. You can fly to all different, most discovered exoplanets. You can stand on their surface. You can see what, the sky of an exoplanet in like a globular cluster looks like. It's really neat. So I was thinking we could maybe play around with that a bit to see what exoplanet surfaces look like and the different type of exoplanets there are. Another option is there's Universe Sandbox, which is essentially a physics playground. It's a gravity simulator essentially. So you can start with a star, throw in some planets, see how they react, and we can, play around with that to look at some different exoplanet orbits, how exoplanets might migrate and things of that nature. So what do people think? Anybody have any preferences? Okay. No suggestions. That's fine. In which case, services. Okay, so yeah, I'm loading up Space Engine now.
Is the frame rate important, do you think? Like, do you want to do what we did before for Kerbal Space Program to get better frame rate?
Oh, yeah. I
Okay.
forgot about that. Yeah, that'd probably be a good idea. So I can just stream on Discord.
Yeah, and then I'll pull that up and share it to Zoom.
Yeah. What was the Lich?
Let's see, which one was that?
Oh, orbiting pulsar PSR B1257. Yes, we can look at that, assuming it's in the game, which it should be. Yeah, sorry. Things being slow. Building shader cache. Okay. Okay, there we are. Now it's cooking. Okay, so I'm gonna stream this thing on Discord like we did before. Okay. Okay, can you see my screen?
Yes, I can see it. So now I will share that here. There we go.
Nice. Oh god, the computer's having a seizure. Let me see. If I just float it away, maybe that would. Oh, that didn't work. My computer's still dying. You can see that right on the stream. Or is that
You
just
can see it. Yep.
okay? Do you think I should just what's the thing? Restart Space Engine, or do you think this is alright?
I think it looks all right. It doesn't look too bad.
The constant vibration.
No, it's not too bad on stream here.
Okay. In which case, what was the lich again?
That was PSR B1257.
B1257 plus 12.
Yep.
Okay. Lich. A neutron star. Oh, it's really. I go too fast. Okay. There's 3 planets. Oh, dang. Here, wait. Draugr, Poltergeist, and Phobitor. Cool. Okay. So it might be interesting to see what the surface of Draugr looks like. It's the closest planet. Oh god, my computer's dying. Is the like stuttering getting bad on the stream?
It's flickering in and out on stream, yeah.
Yeah, I'm gonna just turn the game on and off.
All right.
Yeah, because hopefully it doesn't. Oh my god, I can't even use the menu. Maybe it's something to do with the streaming. Yeah, I'm just gonna turn Space Engine on and off again. Okay, maybe it would be better if I actually share my screen, because maybe the streaming is the thing that made it flicker.
You want to just share yours directly through Zoom?
Yeah.
Okay, that works.
Okay. Share screen, space engine, share. Here we are. I hope it doesn't flicker. Oh, yeah, it doesn't flicker. Okay, that fixed it. Good. Okay, so we're standing on Draugr, discovered in 1994. Mass of 1.5 times the mass of the moon. Gravity 0.3 times, 0.3 g. Milky Way is over there. And where's the neutron star orbits, actually? Oh, it's over there. It's really actually small in the sky, isn't it? Yeah. Any other fun suggestions for where we might want to go or investigate?
We could take a look at 51 Pegasi b.
That is a good idea. 51 Peg B. Whoop. Oh, that's a bright boy. Okay. Oh, that's really cool. Right. So here you have 51 Pegasi b, a Taurid sub-Jupiter. I don't know entirely what that means. It's in 1995. You can see it's really close to its host star. It has a temperature of 900 Celsius. Distance from the star of that's a lot of digits. I should probably put that negative. But it has an orbital period of 4.2 days. You can actually see over here. One side is super hot, which is why it's literally flaming. The other side's a lot less so, but still warm because the wind distributes the temperature. You can actually see this blue sort of line behind it, which is the gas flying off into space because of the solar wind of the star.
Yeah, I think I forgot to mention while I was talking about it that it is tidally locked, which is pretty typical of planets that are so close to its star. So it's like a little bit further than a tenth of the distance of Mercury to the Sun. That's how close it is. So it's totally tidally locked.
And if you actually look over here in the game under solar day, it's actually infinity because its day is forever because it's tidally locked. Yeah, and actually, if we accelerate time a bit, you'll actually see that the trail of gas is actually always away from the star, which is pretty neat. Another thing we might actually find kind of fun is if we actually go not onto the planet because it doesn't have a surface, but see what it might look like closer down. Okay, we're beneath the main cloud layer, I think. We just rise up a bit. Yeah. So you actually see the sky is a bit blue here because of the diffraction in the atmosphere. And if you look up, you'll see that this star is actually kind of huge.
Yeah, so 51 Pegasi, even though it's kind of credited as being the first main sequence star discovered with an exoplanet around it, I think it's technically a subdwarf. Its spectral type is very, or maybe it's more considered to be the first sun-like star. And so the spectral type is the same as the sun. It's a G2 spectral type. So for anyone that doesn't know, that's basically a yellow star. That's what the G and the 2 represent, and that's both the sun and 51 Peg. But the sun is G2V, and the V means that it's in the main sequence. And I think 51 Peg is 2-4, which is for a subdwarf. Sorry, a subgiant.
Yep, that's exactly what it shows over here. All checks out.
Yeah, did my research.
Yeah,
an hour before the meeting.
Yeah, anyway, I appear to have got myself trapped. Yeah. Okay, there we are. Okay, unstuck myself.
Another suggestion we had in chat is Kepler 1625b.
Dash I. The exomoon, the moon. Oh my God, it's here. I didn't know that.
Ooh.
Oh my God, it's here. Okay. Yeah. So, was this in? Did we talk about 1625b-I this year? Or was that last year?
I think that was last year.
Yeah, I think it was
Yeah,
during the moon, whatever
Yeah.
competition.
Yeah,
yeah.
it was during our
During
March
the,
Madness
Lunar
moon
Lunacy
bracket.
last year.
Mhm.
Yeah. Yeah, 1625b-I is potentially the first exomoon discovered, which is a moon orbiting around an exoplanet.
I think the most recent observations kind of suggest that it's probably not in existence. But we can dream.
Mm.
Yeah.
It's probably
One-
not real, but it'd be really cool if it were.
Hey, but it says discovered date 2017, so that means it must be there.
Of course.
Space engine wouldn't lie to me. Anyway,
Discovered but not confirmed.
it says transit. Wouldn't lie to me. Anyway, yeah, so Kepler 1625 is a yellow dwarf, a G6V type star. Kepler 1625b is a warm super Jupiter. About, I think that's the mass of Jupiter sign. Yeah, so it's 3 times the mass of Jupiter. Has a period of about 287 days. And 1625b-I, our hypothetical planet here. You know, I'm pretty sure most of the numbers here are just like R and G. Like they're not actually. We can't actually know all this information. Like that's the warm super Neptune. I don't think we know that. It does look pretty. Oh yes, it's a super Neptune, so we can't stand on the surface because there's no surface. Okay, I'm flying out of here. Yeah. Colors are interesting, but I wonder if they're actually true to life.
Does anyone know how we discovered the exomoon? I remember one method we talked about in...
It was I think it was with the transit method. So
Yeah, I think we found the planet with the transit and then noticed another smaller dip. And we're like, was that another thing also transiting this thing that's transiting this star?
I think we, also, aside from another dip, just like a slight variation in the amount of time of the transit that was expected. So that like that kind of the unexpected amount of time for the transit or for the entire orbit could have been caused by another object in orbit of that object.
Yeah, I remember one method that we talked about in Astro 390 was if you have a large enough moon orbiting a planet, then you get that same effect where like they're orbiting around their common center of mass. So if you have a large enough moon around the planet, then the planet is kind of wobbling around that center of mass, which can either make its transit in front of the star happen either ahead of or behind schedule slightly, because it's going to be the center of mass of that planet moon system is going to move around the star constantly. But if it isn't like synchronized perfectly with the movement of the planet and moon, then the planet will either be on one side of that center of mass or the other each time it passes in front of the star, which would change the exact time that it transits. I don't know if that's how this one was potentially
I think that was
detected.
it.
The wiki page for Kepler 1625b-I doesn't seem to give any information about how it was discovered, but it does say that it was theorized that it might have its own moon.
So
But
an exomoon.
Yeah, but then reanalysis of the data last year suggested that it wasn't real.
So there's no exomoon or exomoon moon?
No, most likely no.
That's unfortunate.
Moon